Hello, welcome back. Today we're doing combination sum. Given an array of distinct integers candidates and a target integer target, return a list of all unique combinations of candidates where the chosen numbers sum to target. You may return the combinations in any order. The same number may be chosen from candidates an unlimited number of times. Two combinations are unique if the frequency of at least one of the chosen numbers is different. The test cases are generated such that the number of unique candidates to sum up to target is less than 150 combinations for a given input. Okay, so there's only 150 combinations for that given input. Okay, great. So I'm actually not sure. I'm more familiar with this in code than it is in diagrams. I don't even know how to diagram this, to be honest, but let's take their example, 2, 3, 6, 7, and the target is 7. And the way you can sum it is 2, 2, 3, and a single 7. So I guess the way that I think about it is there's a branching number of choices that you can have, and that branch goes essentially, if I'm at this 2, I can choose this 2. If I, yeah, I can choose this 2, or that 3, or that 6, or that 7, and I'm going to iterate through these until I reach a breaking point. And I guess what I mean is, if I choose a 2, like this is one of the new candidates. Well, I can choose a 2 again, right? I can choose a 2 again. So this will equal 4. This will equal 6. Choose again, and this will equal 8. Okay, so I'm out of bounds here, and I can basically stop, right? But it's quite possible instead of choosing that 2, I chose a 3, right? That's actually equals 9. It doesn't work. I choose a 6, and that equals 12. Choose a 7, and that equals 7 plus 6 is 13, right? So these are all too large, right? So what if I went from here and chose a 2, right? That would have been equal to 6. Chose here and chose a 3. That would have been equal to 7. Okay, so I did find one path, right? This 2, 2, 3 is one path that I found. And I'm going to put this into a results array. Okay, and choose a 6 and a 7, and I know those are too large, right? And I start here in this 2. What if I chose a 2 here? Well, I actually don't have to do 2 at this point. I only have to do 3, right? Because the 2 branch is actually this way. Right? The 2 branches this way. So here, if I chose a 3, 2, 3 would have been too much. So I guess, yeah, this is a terrible diagram. So going from 2s, I can go from 2 on, right? And then going from 3s, I can go from 3 on. 6, I can go from 6 on. 7, I can go from 7 on. And once I find a path, I can add it to a results array. This is a terrible diagram. This might be easier to look in the code, actually. So let's just look at what we have here. So basically, if I'm given, let's say there's a go function, make that pass, and then I call go with some, what do I need in go? I guess I need the remaining target, right? And I guess I need a start index. And that start will be started at 0, and we'll increment it. And then the remaining will start at the target. We're going to have a results array, and we're going to return results, right? So what do we have to do? So from go, we want to, well, I guess we need to accumulate this, huh? In some way, right? So if there's a base case then results append the current, I guess, array that we're populating. And I don't want to mutate that on the results accumulation, so I'm going to copy it. And what is the base, right? Well, the base is if remaining equals 0, I'm going to do that, right? And actually, if remaining is smaller than 0, I'm just going to return out of this function. So what do I have to do here? So just like I said, we have to iterate through these numbers. So for start, for I in range start to, I guess, then we want to make some changes, right? And that means that we're going to have a new remaining, and that's going to be remaining minus this value. We want to call go with start, and start's going to be this I right here, and remaining will have a new remaining, and the current, we can make a new current, right? And the new current will be, everything, well, the new current's going to be everything that we have so far plus this value, right? So the new current will be this. Okay, so what we have here, let's go line by line. We're going to get the length. We're going to create results. We're going to have a go function. The go function is going to check for remaining because we're going to decrement the remaining downwards. If it's lower than 0, we're going to return. If it equals to 0, then we know that we found a valid path. We're going to append that to results. We're going to iterate through from start, which is an index, to the end candidates. And the reason we do that is because when we're branching off, let's say branching off from the number 6, we don't want to branch back to the number 2. We want to branch by only the number 7, right? Only the remaining. So we're going to have the start index, and that's going to make sure that we don't go backwards. So we're going to go from range to start to in candidates. We're going to get the value. That's candidates at I. We're going to find a new remaining. The new remaining is remaining minus the value, and the new current is the current plus this, which is an array concat operation that returns a new array to us, right? And then we're going to call go with that new current. Always important to look at syntax. Let's test it. Okay, so for memory, we beat 97% of people. Great. For runtime, we only beat 19. Now, what are we doing here? For memory, we're actually creating a lot of memory. And the way that you know that is we're creating arrays all over the place, right? So look at this go function. We're creating an array when we append this copy of the current. I don't know if that's avoidable, but we are creating a new array here. And then for here, we're creating a new array for new current, right? New current here, you see that is going to create an array, and then we're going to pass in a new array. I think it's very readable. If we had persistent data structures, I believe maybe Haskell or something that had persistent data structures would make this more efficient. We're using Python. We can make this more efficient by possibly using backtracking and just and maybe mutating the current array instead of changing it here, right? So the way that we think about it in backtracking is I'm going to comment this out, and I'm going to mutate and unmutate, right? So I'm going to make a change, and then I'm going to take that change away. So the operation for this go function will be treated as if nothing happened, essentially, right? You can think about it in that way. Or it's a non-destructive operation for go functions that are outside of this for loop, or at least the next iteration of this for loop. So what am I talking about? So cur, we mutate cur here, right? We're not going to make a new cur. We're going to say cur append val. We're going to pass in the existing cur, and we're going to do cur pop. We're going to pop that val off, right? And I'll trust that this go function also doesn't change cur. So I'm trusting that this pop is going to pop out the exact thing that was appended here, right? We're going to mutate basically with this plus var. We're going to unmutate this minus var. We're going to take the var out. So let's see if this works. Cool. So if we take a note, runtime is 63 milliseconds, memory is 16 megabytes here, and then runtime becomes 53 and memory becomes 16. I think this is just kind of rounding error, but we can see that we're not creating this extra array, right? We're taking a reference to that existing array, we're making changes to it, and then we make sure that we unmutate it. So this go function isn't a destructive, or this append won't change it on things that are outside of this call stack, right? So when I get to the next iteration of this for loop, let's say the for loop goes from index 0, 1, 2, then at this point, at 1, we don't get all those appends from the for loop that was at this 0. Anyway, this is a way to solve it as well. I believe the one before was clearer for me. But everybody has their own preference here. I don't think I can optimize this part, this copy, but you know, they said there's only 150 combinations. There's only going to be potentially 150 combinations of the copy. The worst case, it's that 150 that's going to be copied over. All right. Sorry for the terrible diagram. I wish I could diagram this better. I'm not sure how to draw backtracking, but you know, I think maybe one thing I could have tried drawing is to mutate where we're adding the value, we're calling a go function again, right? We're doing the recursive function. I'm just going to say recur there, and then we do the unmutation, which is taking the value away. And then this combination, we are trying to trust that it allows us to use the same array in a predictable fashion. Okay, thanks a lot. I will see you on the next one.